Principal Program Manager, Manager.
So senior Director of BI and Analytics at Microsoft.
Strong useless type.
The most watched YouTube video for data science on YouTube right now. So he's got 310,000 views on his intro to R video. So that's probably a more important title than the senior director.
Yeah, that's probably, yeah, agreed. Agreed. So before I get started on the deck content, I do want to offer a quick thank you to the Data Science Dojo folks for hosting the meetup tonight, and thank all of you for coming to actually hear me talk. Hopefully it's worth your time. I really hope that to be true. I do want to say a quick something about Data Science Dojo. So I first met Fook and the founder of Data Science Dojo, who's not here today, a gentleman by the name of Raja, a couple years ago. I was a student in one of their week-long boot camps, data science boot camps. And they're good guys. We've been in contact. We've done some things over the past couple of years together. There'll be a funny story about Fook coming up here in a second. So all I would say is that they're really great guys. And if you're interested, quite frankly, in bootstrapping into some data science skills and then applying them immediately in your daily work, you may want to talk to Fook or somebody after the meetup about their boot camp. It's really good. I've done it. I've taken it. I can attest to it. It's good stuff. So thanks, guys. Appreciate you guys hosting tonight. Okay, so quick intro. As Fook said, I'm a manager guy. I work in Microsoft's IT department, where I manage a technical program management team, where we're responsible for the data platforms used by Microsoft's manufacturing and supply chain organization to execute their business. So these are the people that are responsible for building Surface Studio, Surface Pro, Surface Book, Xbox One, mice, keyboards, anything physical that Microsoft makes. They source the raw materials, they get it manufactured, they get it to market. We provide the data platforms that they use to get all that work done. I've been in IT for 20 years, the last 8 of it at Microsoft. To be honest, there's a 2-year stint in there where I actually worked on SQL Server. I shipped features in SQL Server 2012, but mainly I'm an IT guy. And I do need to talk about this last bullet point. I'm sure some of you saw the meetup and said, okay, #1 data scientist on YouTube, boy, this guy's got a big ego. He's really full of himself, isn't he? You can blame Fook for this. I get an email out of the blue one day from Fook saying, essentially, Dave, you're famous because there's a website called ktnuggets.com, and they're a data science portal type website. And they had an article stack ranking the most popular videos on YouTube by views, and I was at the top. So the point of bringing this up is not to stroke my own ego, but to say, look, I have some videos that maybe you might find useful. So if you're interested, go find my channel on YouTube. Okay, but enough about me. Let's talk about what really matters. What's in it for you? Why are you here? Why are you giving me an hour and a half of your time? Well, there's a few goals that we have for this presentation today. Obviously, the first one is to get you introduced to the concept of event log mining and maybe some of the art of the possible. But more importantly, and I'm hoping lots of folks take me up on this, is to get some hands-on experience. The bulk of this presentation is going to be in Visual Studio. It's not going to be PowerPoint. I hate PowerPoint. I like code. So it's going to be mostly about code. So I want to give folks the opportunity to get some hands-on experience, either maybe right now, or maybe you watch the YouTube video later and you walk along, or you just grab the file whenever from GitHub. But working with this stuff is super important. That's how you cement the concepts and start to learn it and actually apply it in your daily work. And lastly, and I think most importantly of all, and if I seem overexcited, I apologize, but I would really, really love it if everybody went to work tomorrow, grabbed some of their data and mined it, and then sent me a LinkedIn message saying, Dave, I mined my data. That would be super awesome, right? Because data science is about doing, right? It's not about talking and doing PowerPoints. It's about actually doing stuff. Now, that being said, I do want to clearly articulate a few non-goals. This is the PM in me coming out, unfortunately, what the non-goals are. I'm not going to teach you R programming tonight. That's a broad subject, obviously. Way too much to talk about. Also, we're not here to debate the hows and whys of the best way to do things. I am using read.csv. If you find that offensive, okay, let's talk about it after the meetup, not during. Okay, that's all right. Next up, we're not going to talk about specialized scenarios. Let's say you say, hey, Dave, I got 32 TB of event logs I need to mine, for example. How do I scale that? How do I scale these tools and techniques? It's a valid question, super important. We're not going to talk about it tonight. As you'll find in the next slide, the reason why is that event log mining can actually be applied to a broad range of scenarios, which makes it so cool and exciting, I would argue. So it means it works on event logs of all shapes and sizes. So we're going to tend to focus on the 80%, right, of the breadth rather than the depth. At the end of the deck, there will be some linkages where you can go find out more about how you scale these tools and techniques to Hadoop scale data, but we won't be talking about that tonight. And lastly, you won't be a process mining algorithm expert. Do not put this on LinkedIn on your profile after tonight, please. The main reason for that is I am not an expert in process mining algorithms, therefore I am not qualified to make you one. I have studied this stuff quite a bit. I think it's very fun, interesting, and exciting, but it's more of an introduction. Okay, why mine event logs? So I'm a PM by trade, so I tend to think of personas and scenario-focused engineering and all that kind of stuff. So I like to think about it from the various types of data personas that may be interested in answering particular questions. So first up, if you're a business or a data analyst, let's say you have a workflow or a business process that's not performing up to business goals, it's not performing up to KPIs. You may form a hypothesis that says, despite our best efforts, I think the folks executing this workflow or process may not be doing it in an optimal manner. How do you validate that hypothesis? You can use event log mining, to find out what's actually going on, how the process is actually being executed, and you can validate whether or not that's true. Potentially more importantly, and this will be a common theme you'll hear me talk about during the presentation tonight, is you also may be interested in the variance. Maybe everyone's actually doing everything in a reasonably okay manner, but there's too much variance based on factors like season, right? Or during Christmas time, maybe we take some shortcuts because we're just super busy. Or geography, maybe not every part of the org and every part of the world is doing it the same way. Product line, maybe we're varying based on the product line that we're, whether it's TVs or, CD players. Oh my God, how old am I? Sorry. DVD players, etc. Right? Okay, so there's a lot in it for a business or a process analyst. Now, I am a PM by trade. I manage a team of PMs. I extol my team that these tools and techniques are extremely valuable to product and program managers because you care about your system, your service, your application, your website, all up, end to end over time, right? These tools and techniques are extremely important for saying, okay, as an owner of this system or product end to end over time, how are people actually using it? How does that vary over time? As I release features or if the business changes or a marketing campaign happens, how is usage potentially getting better or worse or just potentially changing in some way? Very, very powerful techniques for program and product managers. And lastly, the much ballyhooed data scientist. What's in it for these folks? Arguably, they may get the best benefit of all because an event log essentially is a big flat file most of the time, right? It's just a big file filled with stuff. And you can run various types of summary statistics over it, and you can slice it and dice it and visualize it with ggplot too, and all kinds of good stuff, and that's absolutely useful. But there's a thing called Anscombe's quartet. How many people are familiar with Anscombe's quartet, right? It's essentially this thing in statistics where a statistician said, look, I can have 4 very disparate collections of data that all have exactly the same summary statistics, but when I plot them out visually, they're not the same, not even close. So summary statistics are extremely valuable, but they are insufficient on their own. This is where event log mining comes in, right? I can look at an event log and slice and dice it in lots of different ways, but can I get the moral equivalent of Anscombe's quartet? Can I visualize the data in such a way that the very important aspects of the data pop out at me? And this is super important because in the end, data science is all about feature engineering, right? How do I create new features or derive features from the existing data that make my models, my machine learning models, as accurate or as efficient as possible? So this stuff is extremely useful if you're looking at event log information for that. For a data scientist to look, get those synapses firing and saying, ooh, here's a bunch of cool features I should engineer and try out. So potentially data scientists benefit the most. Okay, so most of you are still here, so I'm assuming you're buying what I'm saying. So I will offer up that for the next 90 minutes or so, we're going to have a particular worldview. And the first thing that we're going to assume in this worldview is that everything's an event. And I mean everything. Because What I want you to do is get into that lens, that frame of mind where you look at the world and everything's an event. Because then these tools and techniques, you'll start saying, oh, wait a second, I could use it here, I could use it there, I could use it there, I could use it all over the place, right? So everything's an event. I've got some examples here, non-exhaustive, but let's talk about one, for example, in the middle, IoT, because it's all the rage. So I'm a farmer, and I have crops, and I have sensory devices across my fields to alert me to frost conditions, let's say, right? Every time one of those IoT devices takes a temperature reading, that's an event. I mean, essentially, you could say that IoT is nothing more than just a whole bunch of events coming in from news sources, right? It doesn't have to be web server logs anymore. Now it's little small devices also, but they're all just events, right? All just events. Lots and lots of ways, right? So I would argue that a corollary to that is that if you think of everything as an event, because it's wildly useful from a data science perspective to think of the world as just a bunch of events, then everything that's an event can and should be logged. Because if you're not logging the events, you're not getting the raw materials to mine. And that's what we're here for. We're all about the mining, right? We love to mine. Now, what that also means, too, if you buy this worldview and you say, look, you know what? I believe that Dave's onto something here. Well, I shouldn't say Dave. Actually, it's the folks at the Technical University of Eindhoven. But if those folks are onto something, and I should add this to these tools and techniques to my data scientist tool belt, then I should also think about all of my work going forward in a new way. So, for example, anytime I build something new, I should architect and design for event logs. If everything's an event and it should be logged, I should architect and engineer my systems to spit out lots of event logs of different kinds. If I happen to use off-the-shelf commercial software, SAP or SharePoint or Oracle ERP or whatever, I should configure it for maximum event logging. Any out-of-the-box feature that produces event logs, I should turn on. Right? The traditional reason why an IT guy would tell you not to do that is because storing data costs money. No. Storing data in Azure or AWS or wherever is super cheap. Just get the data, store it, it's fine. Don't worry about the cost of storing it, right? Focus on creating business value that more than justifies the cost of storing the events in the first place, right? And then lastly, and this one's actually particularly important, is as a data scientist, as a product program manager, as a business data analyst, demand event logs. Hypothetical situation, I've got a .NET Stack legacy system, right? And maybe the app tiers were built before the importance of event logs was understood. And nobody wants to pay or take the time to retrofit that system. What can you do? Well, most in-tier .NET applications end up using SQL Server in the back end most of the time, right? So there's a feature in SQL Server, as an example, called database audit specifications. You can go to your DBA, ask them to turn it on, and all of a sudden SQL Server is now logging every single query issued against your database to a log file. Super awesome. My team, we do this for our data warehouse. So we log every query in the supply chain data warehouse that's issued against it. Super interesting. We were able to tell all kinds of interesting things like what data gets used, what data doesn't get used, which orgs use our data, how they use it. I mean, it's just beautiful, right? So, you know, if the worst case scenario, go to the lowest layer in the stack and say, I demand event logs. It's good stuff. Okay. Whoop. Sorry. Okay, so I'm going to go through a contrived example, mainly because we need to learn some common terminology. There's a lexicon of terms in event log mining. It's important because the APIs and the tools use all of this phraseology, so you kind of need to know it as the lingua franca to actually be productive in those tools and APIs. So what we have here is obviously a screen print from Excel. And what this contrived example simulates potentially is maybe a weblog, right? Because if you're familiar with .NET technology, these are all ASP.NET web pages, right? So maybe this is coming from an IIS web server or something like that. That's actually immaterial. What is important is understanding what are the minimum pieces of data that you need to actually do event log mining, and how you would map those minimum requirements to a particular file that you may have at your disposal. All right. So first up is an activity, right? An activity is nothing more than a well-defined thing in a workflow or a process. In the aforementioned IoT example, taking a temperature reading, that's an activity. It's that's what I'm doing. I'm doing something. I'm taking a temperature. Next up, and this is like super redundant, You need a timestamp. Because without a timestamp, just an activity in isolation isn't particularly interesting or useful, right? So you need some sort of temporal aspect to the data. Next up is a resource. Now the resource with a question mark is portrayed that way because a resource is actually an optional data field. It's not necessarily required for event log mining, but it's super useful. And the reason why I wanted to call it out is that you can make an argument that the data center is a resource, because if you think of a resource as people or capital or equipment or computers or what have you, things that are used or consumed in the execution of an activity, that's a resource. So you could make an argument that the Phoenix data center in this contrived example is a resource because I'm using the facilities, I'm using the hardware, I'm using the power, the cooling to serve up these web pages. Now what's interesting is that you could make an argument that the site version could also be a resource as well. And that's more of a judgment call as a data scientist, right? Is for you to maybe you run two analyses, one with Phoenix as the data center as a resource, and then the other is the site version. Resource is immensely useful but optional. The next concept that's important is the idea of an event. Every row in this contrived example is an event. And for our purposes, how we define an event is very simple. It's the combination of an activity and a timestamp at a minimum. That's an event. So it's kind of a higher level construct that marries some of these more primitive aspects together. Next up is the concept of a case. And a case essentially is yet another higher level abstraction that buckets the data together in a particular way. Cases are super important because what they do is they provide business and analytical context to individual events. Now, I use the example of a web session here precisely because it resonates with a lot of people, right? So this user came in and hit 3 distinct pages as part of one session. And we don't need to worry about how we define a session, just know we have to find some way of bucketing these things together. Maybe it's by time, maybe it's by social security number, maybe it's by some other sort of identifier, some sort of correlation ID. Doesn't really matter, but we have to have it because analysis over these 3 things together is what's interesting. Just a long list of events, all you can do is just do summary statistics over it. That's basically all you can do with it. Okay, so you can see here we have 3 cases in this hypothetical contrived example. Not surprisingly, the whole thing is an event log. And I tried very hard not to use the word event log until I actually clicked up that animation. So the whole thing's an event log. Yay. Now, the last concept that we want to talk about is this idea of a trace. And a trace essentially is a distinct pattern of activities that appear in one or more cases inside of an event log. And why a trace is important is because it is a high-level concept to understand variability. As I mentioned earlier, variance and variability becomes an important aspect, an important consideration when you do event log mining. So a trace essentially is nothing more than a distinct pattern of activities that occur in a case, and they usually occur multiple times in an event log because a lot of times you have a happy path or a golden path that people do over and over and over again. That's one instance of a trace, and you see it multiple times in the same event log. Now, this contrived example is bad, 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 by design, because it has the worst case scenario that you can possibly think of. I have 3 distinct cases, 3 distinct traces. I have no happy path. I have no golden path. All I have is everybody does something different. Now, generally speaking, I can't think of many instances where that's actually going to be ideal from a business perspective. Right? That you have such high level of variability of people just kind of like doing everything all the time. It's probably not good. So that's part of the reason why I built this contrived example is to call this out, right? High levels of traces, right? You know, if you think of this as a ratio, what's your trace count divided by the number of cases? As it approaches 1, either super interesting or super bad, depending on how you look at it. Okay, so enough about that. Let's talk a little bit about the data that we're going to work in the demo. So the data that we're going to look at tonight comes from the 2014 Business Processing Intelligence Challenge, or BPIC. So BPICs are competitions that are run out of a technical university in Eindhoven, Netherlands, very popular in the business process management community. What's interesting from an event log management perspective is they tend to have real-world event logs as the source data that they use in the competition. So If you're interested in learning more about event log mining and you don't necessarily have access to your own event log data, you can go find the BPICs and grab their files and play with them. So this is what we're going to do tonight. In this particular example, we're going to look at a subset of the 2014 BPIC, focusing mainly on the incident management activity event log. So for those of you who are not familiar with incident management, it essentially is a IT operations process that says something's broken, fix it. There's a more formal definition, but that essentially is the gist of it. And in particular, this is the event log from a Dutch financial institution called Rabobank. So given our previous slide, right, we can map the 3 minimum things that we need plus the one usually interesting optional thing to this data file. So the incident ID is our case ID, because what it does is it stitches together all the activities into a logical unit. For analysis, a logical unit of business. We have the date stamp, obviously that's the timestamp, and then we have incident activity underscore type. That will correspond to our activity. That'll be things like open, close, assign, reassign, that sort of thing. And then lastly, assignment group, which is the team. So team are people, so they're resources, right? And the rest of the data could be potentially interesting, but we'll basically ignore it for tonight, just to keep things simple. Okay. Yay, code. All right, so folks were asking about this in the beginning. What I've got here is what's known as a Azure Data Science virtual machine. And the reason why I'm talking about this is not just because I work at Microsoft, but because, call it arrogance, but I value my time quite highly. So what I'm interested in is when I need to get some work done, I don't want to fiddle with installing and configuring software, right? I want to get my tools up. I want to be able to do my work. I want to get my value, my insights, and then put them into action. So this is very useful for that because the Data Science VM in Azure comes pre-configured with a bunch of stuff on it. It comes with SQL Server 2016 with our services pre-installed and configured. It comes with R and Python tools for Visual Studio. It comes with Anaconda pre-installed. It comes with R pre-installed. It comes with Jupyter Notebooks pre-installed. It comes with a lot of stuff pre-installed. Not only that, but you'll notice right here, I got 28 gigs of RAM at my disposal and 8 virtual cores, which is more than what I've got on my laptop, right? So I've also got horsepower. I can go in and spin up, not only do I save time, based on the fact that I don't have to install and configure all the software, I save time because I can go grab a piece of hardware, virtual hardware, that's bigger than anything I may need, because then I don't have to worry about running out of RAM, I don't have to worry about running out of proc, right? I can just say, just go off and do my stuff, get my insights, shut it down when I'm done. Okay, enough about that. So what we have here is Visual Studio. I have used Visual Studio in my career for a very, very long time, so I'm really familiar with it. There's nothing in here that is Visual Studio specific, by the way. So it's standard R code. I just happen to use this IDE because I like it, not because I need to use it for anything. So the first thing that we're going to do is we're going to load up the packages that we're going to use in this analysis, right? And the first one I want to call out is this function, or this package called EDEAR. I'll call it EDEAR for short. So EDEAR is a specific package specifically designed for analyzing and mining event logs. So it has a lot of helpful functions to do good, cool stuff in analytics with event logs. So I want to call that out. So we'll just go ahead and run that real quick. Next up, I'm just going to load the data, and then I'm going to pull up the structure of the data so we can take a look at it real quick. So as we said before, right, there's a bunch of fields. Well, I should say a bunch. There's a few fields in here, some of which we care about, some of which we don't, right? So here's our incident ID, and we have a few examples of what that looks like. And then we have a timestamp, a few examples of what that looks like. And then we have our activity. And you can see here's some examples, right, of what that looks like. Okay, cool. So what we do notice, though, is that everything's essentially as a string. It's all character data. That'll be important. Well, not all of it. Obviously, the date timestamp is something other than character data. So we're going to need to fix up some of this data. So the first thing that we're going to do is we're going to use the package called Lubridate. And if you're not familiar with it, Lubridate is a collection of utility functions that makes working with time and date data much easier. It's by a guy by the name of Hadley Wickham, who's probably like the most prolific and important R guy in the world right now, because he writes lots of good packages that you'll use all the time. So we'll go ahead and run that. And you'll notice here that I've explicitly called out, even though it's the default on the function, that we want to assign a UTC. We want to assign a time zone, because we'll see here, right? There is no time zone assigned to these things. And that's the bugaboo about working with event logs or anything with time aspect to it, right? Is you got to start worrying about time zones and offsets and that sort of thing. So we're just going to force it to treat everything as UTC, even though in the data there is no time zone. It's just we're just going to normalize it to UTC. Okay. I'm going to go ahead and transform all of the rest of the data, because it's all string data, into factor variables. It's all categorical data, so I'm just going to make them explicitly factors with this code. Now, the last line, while this runs, deserves some explanation. This last line here, right? I'm adding a piece of data to the file called lifecycle. All that is syntactic sugar. An API that we're going to use from Edir requires that there is a column, a variable in the data frame for lifecycle. We're not even going to plan on using it, but we're just going to make the API happy. So it's just, it's our programming. This is the way it goes. All right, so we're setting up our data now. We've got some factors and everything. So one thing that we should notice real quick here, let me pull up the incident data. All right, so this is just literally a tabular view of that data frame. You'll notice here that we've got many, many events associated with the same case ID, which is what we expect, right? But what's particularly interesting is look at the dates. So the first one is January 7th, 2013. The next one is almost 10 months later, right? 11/4/2013. That's super interesting. By the way, you're going to hear me say that term, super interesting, a lot, and I apologize in advance. If you watch my videos on YouTube, I say it all the time too. I find everything super interesting. This is particularly interesting because what that tells you is something that happens a lot in event log mining, that you may have a process or a case or a set of activities that start, and the amount of time between them can vary quite a bit. And we got 10 months here, right? So sometimes what we need to do is say, look, I want to analyze the data obviously at this fine grain with all of the disparate date timestamps in it, but I also may want to do some aggregated analysis. So I need some way of normalizing this, right? I need some way of normalizing and say, look, yes, there's almost 10 months between these two, but what I really want to do is categorize the fact that this case started in January. It is a January case. And maybe I can compare it to all the other January cases to say, do all the January cases take 10 months to run? Yes or no, right? That sort of thing. The other thing I do want to call out, which is also very common, is you look at these two things right here. And if you go over, they have the same exact timestamp. That's actually very, very common in event log mining, is that either because of the way a system is built or because of the vagaries in the data, maybe, for example, you don't have microseconds or nanoseconds or whatever. You don't have fine enough fidelity in your date timestamp. You can't differentiate which one of those things actually happens. So the tools, the algorithms, the code won't be able to say, look, I know that closed always comes after caused by CI because of the semantic, because of the business process. So sometimes we have to help it along. And we have some code later in the file that actually does exactly this, takes care of this problem. All right. So this code right here is going to do a couple things. The first thing it's going to do is it's going to take all of our raw incident data and it's going to group it by our case ID, which makes sense, right? It is our thing that groups everything together. It's then going to arrange that data by the case ID and then by the date timestamp in descending order, right? And then with this particular line of code right here, this is where the magic happens. Ooh. By the way, this is dplyr, if you're not familiar with dplyr. I'm going to ask dplyr to say, okay, look, I've got everything structured in ascending order by case ID and then by timestamp, which means that for any case ID, the first record in that case ID is the earliest. And I'm just going to grab that record. That's what that row number 1 means. Grab me the first entry out of every group that is organized in ascending order, first by case ID and then secondarily in ascending order by timestamp. So that always grabs me the earliest date. And then mutate allows me to create a new data field. And what I'm going to cram in there is a value that I extrapolate from that least date. And I use the floor command to say, whether it's January 1st or January 9th or January 27th, make it all January 1st. I don't care if it's March 3rd, make it March 1st. I don't care if it's July 24th, make it July 1st. What that does is just basically allow me to normalize into a month and a year, because the day will always be the first of no matter what. So now I'm just narrowing the variability of that particular variable down to month and year. And that allows me to do the analysis I talked about earlier, which is give me all of the January cases, all the cases that started in January, so I can actually do some analysis over those. Give me all the ones that start in February, so I can do analysis all over those. And then lastly, I just select the incident year. So what I'll do is I'll run these 2 batches of code, and I'll talk about the second one real quick while that's running. So the first batch of code that we just went through creates a distinct list of, IDs and the months, right? This case starts in January, this case starts in February, this case starts in March, so on and so forth. That's a very normalized short list. What I then need to do is then go back into my big long list and say, for these 27 events associated with this case ID, I need to make sure that I assign the right month ID to month year ID to all of those. So that's what the second batch of code does. It actually does a left join and says, look, take the big log file, and everywhere where the incident IDs are the same, match them up. And then you'll see here, for example, if I run this line of code, you'll see right there, let me pop this up a little bit. You can see that this is some of the first entries now, right? And you can see January 7th, the 9th, and then September 25th, and then November 4th. But they all have the same start month year. This is a January case. This is what this variable says, right? Even though it took 10 months to execute, it still started in January, so I'm going to classify it as a January case. This is a very common thing that you do in event logs. Time becomes an extremely important factor. Okay, next up in the code is that API, that pesky API that I talked about that's so cranky. Right? This is the API from Edier that requires the lifecycle. So we just added one just to make it happy, even though we're not going to use it for anything. Because the rest of the functions in the Edier package are that useful if we're going to go ahead and do that. All right. Cool. Now, in fine R fashion, the Edier package offers a summary, an overloaded summary function that you can use on event log objects. What I'm showing here is how you can use the pipe syntax to say, look, I want to take my new incident log that I just created and pipe that into the summary function and give me the results. Alternatively, you could just type in summary, open paren, incidents log, close paren, and hit enter. That would work exactly the same. But if you're a big dplyr fan like I am, you got to pipe, right? You got to pipe. All right, so this will take a second because the function actually has to do a couple iterations over the entire event log file to calculate some of the summary statistics. And here you go. I won't drain this output. The most interesting stuff is here at the top. All right, this is good summary information about the event log, right? A few things to note, right? We have 467,000-ish events. We have 46,600 cases. We have a lot of traces, right? We have 22,000 traces. Now, what's particularly interesting, I would argue, those first three things are reasonably interesting, but it's the next two that are super interesting. You have 39 distinct activities, right? That's your universe of things that are being done. And then the average trace, remember this is where the concept of the trace comes in, right? Out of all the patterns of activities that we see across the entire event log file, on average, they have a little over 10 activities per. That's how long the traces are, which is interesting. Question? Wait. Oh, so very good question. So the question was, what is a trace? Okay, It's kind of an abstract concept. Hopefully I can do it justice. A trace, a single trace is a distinct pattern of activities that show up within a case within an event log. And what this is saying here is that there are over 22,000 distinct patterns of activities that show up. And what you can infer is that since there are about twice as many cases as there are traces, some traces show up multiple times in the event log. Good question. Yeah, so for example, let me try to do this some justice again, like I said. So let's say my activities are A, B, C, and D. Let's say I have a few cases that do A, B, and D. That's one trace, A, B, D. Maybe it shows up 5 times. A, C, D is another trace. Maybe that shows up 27 times. A, B, C, D is another trace. Maybe that shows up 150 times. Each one of those is a trace, right? They're 3 distinct traces. Even though they show up, they manifest multiple times inside the event log. And, oops, sorry, say that again? Essentially it's a grouping. It's a pattern. It's a grouping. It's a pattern grouping and saying I just want to count them all up, right? It's kind of like when you play poker. There are patterns of cards that make hands, and those are distinct things, right? There are only so many numbers of hands that you can make from any particular set of cards. A trace is kind of like a hand. It's a definition of the constituent pieces that make up something that's more interesting. Again, hopefully I do that justice. Yes? I'm sorry, say it again? No. And I say that so definitively because I have a certain worldview. So a cluster implies some sort of, into my mind, some sort of distance calculation in some sort of dimensional space. Yeah, this is not that. This has absolutely nothing to do with distance. Could you calculate something like Jacquard distance? You could, but you don't see any of that in the literature that I've read.
Essentially, it's just like kind of like a poker hand. It's like a very concretely defined concept with basically no, I don't want to say none, but like no ambiguity.
Essentially, yeah. Essentially, you could think of all the activities in the event log as all of the playing cards in the universe, and the trace is just nothing more than particular combinations of those cards that show up.
You have to eliminate some, like I guess, noise creating events from an event log to find unique traces for analysis.
Yep. Yes. And you will see that we will do that twice in the demo. Go ahead. Is the activity ID? The activity ID is not unique, right? It's like open, closed, assign, in this particular event log anyway, open, closed, assign, reassign. It's not unique. It shows up thousands and thousands of times.
Is an activity kind of like poker analogy? Is an activity basically like a card?
Yeah, Jack of clubs, for example, would be, if we're stretching that metaphor a bit far, yeah, it would be like that. Okay. Yeah, and that's what I did in my contrived example, right? Yeah. 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 So some sense about classification. Again, I'm going to be definitive because I have a certain worldview. There's no machine learning here, so it's not classification. You can think of an activity mainly. The best way to think about it, well, I should say the best way. One way to think about it in R is it's a factor variable where each individual string is just one of the levels. So in this particular case, activity could be thought of as a factor. In fact, we did make it a factor. And there'll be X number of levels, and the levels are things like open, closed, assign, reassign, that sort of thing. Yes, floodgates have opened. Excellent. it's potentially every case can have a trace, and that's bad. Remember, I asserted, maybe incorrectly, but I asserted earlier that that was potentially bad. But yes, that could happen. My contrived example was exactly that. Every single case had a different trace. So I had 100% perfect variance, right? The number of traces was equal to the number of cases, which is most likely, in my experience, bad. Bad. Yes. Yeah. So prototypically, it's essentially where the pattern definition is usually thought of as where any particular activity only shows up once. So if I had A, B, B, C, B, B, D, I wouldn't necessarily put all the B's in there, right? But it could be useful potentially to think about if all the B's are close together, right? B, 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 you could just put one B in there and call it good, but you may want to keep the other B because it's separated. You may want to keep that one in there too. So but strictly speaking, the mathematical definition is where they actually show up once. Trace ID, you can use it, I believe, it's a good question. I'm going to talk off the top of my head, and I could be wrong. I believe the editor package allows you to enumerate all the traces. I'd have to look up on that. Yeah. Okay. Great questions. I was starting to get worried. No one was asking me questions. It's like, oh, doesn't anybody care? Okay. So let's go on to some more interesting analyses, right? In the interest of time, I'm not going to drain the dplyr code like I did before. One of the most important things that you want to do after you get some high-level summary statistics like we just did was you want to look at how things are changing over time, right? Because timestamps are so important. Temporal aspects are part and parcel of event log mining and event log analysis. So one of the first things we look at is data over time. For those of you who are fans, ggplot is another Hadley Wickham original. So and here's this term again. This is super interesting, right? So what I have is a case counts. Again, this is based on the month and year of the start of the case, right? So this is all the cases that started in January, no matter how long it took for them to complete. These are all the cases that started in July, no matter how long they started to complete, right? We have a massive spike of cases starting in October. This is super interesting. Why? Because this gets my data scientist spidey sense just going, weep, 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 right? Because this is usually indicative of some big change, right? Some sort of business change. Maybe we got acquired by a much bigger company and now they're pumping a bunch of volume through. Or maybe this is where we actually went live and like Facebook, whoosh, we took off like wildfire, maybe. If that's your startup, lucky you. Or it could be an error. Or it could be an error, right? Most likely human. Maybe people weren't actually following the process right and things weren't getting logged the way they were supposed to because the human beings were doing something wrong, right? You know, part of the reason why I'm an IT guy is because I tend to trust computers more than I do people. So, super interesting, right? Case counts over time. Now, the other thing that we tend to care a lot about is throughput. How long does it take to actually get something done? Now, imagine, if you will, this is an IT operations thing, and while it's interesting, being an IT guy, I think IT is interesting. Maybe it's not interesting for everyone in the audience. But so think of this in terms of maybe like a website. You work on an e-commerce platform or an e-commerce business, right? Your throughput may be super interesting. There's that term again. Because think about the customer journey through an e-commerce website, right? The customer lands. Dave lands on Amazon. And Dave buys from Amazon quite a bit. Dave lands on Amazon. Jeff Bezos is wanting to make sure that Dave's going to give him cash money as fast as possible at the end of that interaction, right? That's his goal. So throughput's immensely interesting from a lot of perspectives, right? You know, how many pages does Dave look at? How long does it take on average for Dave to abandon Amazon? Because he doesn't always buy when he goes, by the way. Not always. A lot of the time, but not always, right? And the time becomes an important feature for analysis and potentially for data science and machine learning as well, So we care about throughput a lot. So what this code is going to do is essentially it's the same thing, but we're going to track the throughput of cases over time based on when they started. So what is the average throughput of all the cases that started in January? What is the average throughput of all the cases that started in February, in March, April, June, July, so on and so forth? And not surprisingly, super interesting, right? Oh, man. Some IT executive, he's getting a lot of love from the CIO if this is the case, right? Because he's trumpeting that big time. So, but again, this is super interesting because while everybody would love to see this, you know, your data science spidey sense would be going, weep, 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 weep. Wait a second. What is behind this precipitous drop? Especially given the fact that simultaneously, we had a precipitous increase in the number of cases. What's going on here? Yeah. Correct. The year, it's a sense of scale. We'll see in a second that this is like 200. Yeah. It does look like 0, which is why, you know, we'll spit out some tabular stuff, right? Just to verify, because the sense of scale just diminishes this, right? Good question, though. Good question. Don't assume that I know what I'm doing. Feel free to ask me questions, right? To your point, here we go. So we're going to do a tabular output here of just the average throughputs, right, by month. And what we can see here is, whoa, heads of command, and it says just give me the top X number of rows. So like in Excel, it'd be like saying just give me the first X number of rows in an Excel worksheet. Okay? So you can see here, big, long time. Ooh, pretty big decline. But I would argue this is a very interesting cluster, and I'll use that term very loosely, obviously, based on what I said earlier. The range in values here is very, very close compared to the range in values here. So I would say, wow, that's probably something worthy of additional analysis, right? And then lastly, to the gentleman's question before, we can take a look at also the output, the table of the actual counts of the incidents by the month and the year. Right, and we can see it's not 0. It's 278 in January, 452. But once again, you'll notice that once you get to here, the range is much closer between these values back here than it is down here. Even though this number is far bigger than this one, it's still not of the same magnitude as the rest of these numbers, which is just another way of saying that may be a potential area where I should focus in the event log to do some more interesting analysis of what's going on. My plot isn't right? So unfortunately, you'll need to take it up with Hadley. Because I'm not smart enough to actually write the code that actually draws the graphic. I stand on the shoulders of giants as usual, so yes. Yes, we're going to be looking at that. We're going to segment down. You're getting ahead of the presentation. Yes. Correct, but this right here, right? It's based on this overall scaling. Now, to be honest with you, I was a bit crass earlier. You can fiddle with all of these axes if you want to try and get them better, but in general, in my work, I don't worry about that so much because I always look at also these numbers as well, right? And as the lady mentioned up here, I'm also going to do summaries. I'm going to get multiple number summaries. I'm going to do quantiles as well. Yeah, potentially. Yeah. That's interesting. That may be a bug in ggplot. 2, maybe. Oh, I didn't even notice that. Hmm. Okay. It's a good point. But like I would say, as I would say, right, we can also verify by just looking at the numeric summaries as well. Right. Yeah. So the point I would argue, though, yes, everything you're saying is absolutely correct. But the point of this analysis is not to necessarily worry about actually what the real values are, but to understand the relative patterns that are going on, right? The fact that this is much, much bigger than this, right? That's really the point. But yes, like I said, keep me honest. Don't pretend I know what I'm doing. Okay, so next up, what we're going to do is we're going to say, okay, look, you know what? Let's filter down the log as we talked about. And I'm just going to run this code and talk a little bit about it for a second. Did that already run that fast? Okay, so we know that we want to look at this section, even though it's not labeled correctly. We still want to look at this section of the data, right? So we need to subset the existing event log object that we created using that API we saw earlier. But the problem is that we need to make sure we do it in the right way so that we don't lose the event logness of the thing that we created, right? To do that, you have to make sure you specifically use ed_ear functions because they always return back an ed_ear event log object. So I could slice and dice this incident, the incident's log object, just using straight up dplyr, but it would return me back just a plain old data frame. And then that wouldn't work with subsequent ed_ear functions because it would say, that's not an object I understand. So what this line of code is doing is saying, look, give me every distinct incident ID that starts in October or later, and give that to me as a distinct list. And then I can feed that into a dedicated ed_ear function and say, subset me the log that way. And then what that allows me to do is keep the event logness of my object. It's just the vagaries of the type system in R. This is something to be aware of. And now, again, this is a proof positive that so don't assume what I'm doing, right? One of the things that's awesome about R is you can do wide sweeping data manipulations with very few lines of code. It's great. It's why it's my favorite language for doing data science. However, it's also very easy to screw up and do very bad things to your data at large scale as well. So this line of code is about just essentially a sanity check to say, okay, do these numbers match up with the previous numbers? And in fact, they do. As a wise manager I once had said, this is why we test. This is why we test. Okay. Okay, so we've got a subsetted log to only this really interesting region over here, right? Now, to your point earlier, let's go take a look at the distribution of the throughput of this interesting area because we know that things got radical from a case count perspective while simultaneously things got radically high from a case count perspective and radically low from a throughput perspective. It's probably worthy to take a look at the distribution of the throughput times for just this subset of data to see what's going on. So again, I use the throughput time function from ed_ear to get back all of the distinct times. And then I can just use out of the box R functions like summary and quantile to get some more information about, oops. Okay, come on, Dave. There we go. Okay, and what we get here is the number summary for, for the distribution, right? So the median in this interesting space of throughput is less than a day, 0.717 days. But potentially more interesting is that we still have some maxes that are pretty big, 175 days. So there's something interesting going on. So this is where quantiles comes in to can be a little helpful, right? Where I could say, okay, look, what are the cutoffs at the 10% of lowest values, the next 20%, the next 30, the next 40, so on and so forth. And what we find is at the extremes is where things get interesting, right? So 90% of the cases that start in October or later are completed in less than 10 days, 90%. But the top 10% look like they may be potentially skewed. And this is actually something that's very, very commonly done in event log mining, which is we tend to concentrate a bit on the tails. So imagine, if you will, you're a retail bank or you're a cellular carrier, right? If you're running your business correctly, the customers that are going to churn, that is, leave you to go to a competitor, ideally is very, very small. If it's not, sell the stock, right? Something bad's happening. So we tend to focus a lot on the tails in event log analysis, right? For example, if I wanted to do event log analysis on the customer journey of somebody who, let's say, is not particularly happy with their cell phone provider, and what I'm doing is tracking the events of how that customer interacts with the business to create a model that predicts whether or not they're going to churn, I will tend to work on the extremes of the event log because, again, that number tends to be relatively small. So, as a consequence, what we're going to do is we're going to split the data again. So, we're going to create 2 new event logs for this late stage area of the original event log, but we're going to use the 90% threshold as the value. We're going to create short ones, which are essentially everything that's 9.287 days or less, and stick that in one event log file, and then everything that's bigger than that in another event log file, and then compare them. To see what's the differences between the stuff in this area back here, which gets done relatively quickly, versus the stuff that takes a long time to get done. That's what these 2 lines of code do, once again using some add-here functions. Ooh, where did I do? There we go. Yeah. Okay, there we go. I won't drain this code because it's just some pretty simple stuff. You could always just look in the help system on it. Just to get some summary stats. And this is where summary stats become particularly useful. As we can see here again, double check, right? This is about 10%. This number here is about 10% of the total. So that makes sense. Good. I didn't make a mistake. But this is a potentially interesting right here, right? Which is shorts on average, cases that start in October or later, that fall into the short bucket, as we define, under 10 days approximately, on average have a little over 8 activities per case, on average. And then the longs, which are everything above essentially 10 days, have 22. And there may be a, well, duh, Dave, moment going on here, but as a data scientist, you don't want to make too many assumptions, right? You want to make an hypothesis and validate it. And what this says is, yeah, it makes sense, right? Obviously, if things on average take a lot longer, I'm probably doing more stuff in general. You could do that as well, absolutely. That's another analysis you could do. We're not going to do that tonight, unfortunately, because of time, but yes, absolutely right. Now back to traces. This is also super interesting. You'll notice that we have a total number of cases for the shorts of about 41,000, sorry, and we have 17,500-ish distinct traces, which is still a relatively high percentage, but it's actually lower than what we saw earlier for the file all up, right? It's still pretty bad, I would argue, but it's not as bad as looking at the file all up. Reflexively, I have a little over 4,500 cases, and the longs have 4,410 distinct traces. So we're getting, high 80s, low 90s, right? If you think of a ratio, bad. Bad. Or, if you're a data scientist, interesting, right? All right, so let's drill in a little bit on that, right? So we've got this new distinction between the late era of things that are taking a relatively short amount of time and stuff that's taking a relatively long amount of time. What do we want to know next? Well, what we probably want to know next is to gain more insight into the structure of these processes, right? What are the activities, how common they are, how often do activities show up, percentage basis in how many cases, that sort of thing. And there are functions from the add-here package that do exactly that. So the first chunk of code here actually runs a function called activity frequency, which calculates the relative frequency of activities in the short event log. And I'm just going to run the head here to get the top 10. And we can see here a few things that are right off the bat that are super interesting. First, assignment is the number one most common activity, with 17.7% of all activities in the short log. The next step, which I think is potentially even more super interesting, is closed and open. More closed than open, and they're not 100%. But now, there's an argument to be made that you could potentially see more open than closed, and that would be okay, because my event log is eventually going to get cut off at some point. So I'm always going to have some orphaned cases that were open right before the cutoff and weren't completed yet. So I could, as my spidey sense tells me, that would be okay, but this seems funky. Right? They're more closed than open, and it's by about about a half percentage or so. That seems interesting. I won't say bad, I'll say interesting. You could have your data could be bad, the processes could be bad, the humans could be bad, right? So there's all kinds of things, right? But I mean, this is where, I just, hopefully my love of event log mining is coming through. I mean, I just love this stuff. It's great. It's so much fun. Okay, next up, let's just do the same thing for the longs. Okay. First thing that pops out is look at close and open. Close and open were the second and third most common activities in the short, and they're way down here in the longs. All this other stuff is above it, which is interesting, but also intuitively makes some sense, right? If these things are taking maybe up as long as 175 days, there's a lot of stuff going on, right? In an IT shop, unfortunately, a lot of times it's like this. It's the database. No, it's the SAN storage. No, it's the OS. No, that kind of thing, right? So this makes some sense to me. Okay. Next up, we can take a look at, okay, how prevalent are activities within the event log, right? Given a particular activity, how many cases does it show up in? What percentage of cases is it present in, right? And this is where things start to make a little more sense, right? Open, 99.99%. Okay, great. Whew. It's above closed. Whew. Okay, that's good. I like that. That makes me happy, right? This just jives with some of my intuition. It's not perfect, but it was better than what I first saw, which was like, wait a second, what's going on here? Next up, we got the lates. Oop, went too far. Sorry, guys. Remember, sound effects are very important in data science. Okay. Yes. Yes. All is right with the universe. 100%. Love it. That jives with the business process and my understanding of it. Close is way up there. This is the aforementioned scenario I was talking about. This makes sense to me. I could have some orphaned records at the tail end of the event log. This wouldn't surprise me. So this is all goodness, right? So this gives me some idea, right? Okay, I know that the shorts don't have a lot of activities. The open and close seem to be much more rigorous in the longs than they are in the shorts. And in general, there's a lot more activities going on between the bookends of an open and closed and a long than there are in a short, which all intuitively makes sense. And you could say, duh, Dave. But again, as a data scientist, you want to validate your hypothesis with the data. Okay, so to an earlier question, we spend a lot of time in event log mining filtering. Filtering. Because here's the thing. It's very, very common in event logs, especially event logs of any sort of size, that there's a lot of outliers. There's a lot of variance, there's a lot of variability, right? And usually what you're trying to get, at least in the early iterations of the process, is a general handle on what's going on. And so a lot of that stuff just becomes extraneous noise. So you tend to filter it out. You may add it back in later as part of subsequent analyses, but in the beginning you tend to filter down. We're actually, as I said earlier, we're going to filter twice. This is the first one. So in general, what you typically do in event log mining is the 80-20 rule, or in this case, the 90-10 rule. I'm going to take the top 80% of stuff and look at that first. If I need to, I whittle that down to the top 80% of that, and so on and so forth, until I get a good, interesting understanding, or hopefully hopefully if you end up with no data, then that's a problem. But assuming you don't end up with no data, you gain a good understanding, and then you can work your way back up the stack with subsequent iterations and incorporate more back end. So we're going to create a couple of event logs there. Now, I mentioned this code earlier. I won't drain it because it's quite long. But all this code right here is actually the code that, I'm just going to run it while I talk, is all the code that goes in and says, look, organize all of the event log data in ascending order of case ID and by date, so that I always have, the earliest date at the top and the newest date at the bottom. Find out what those values are, store them for a second, and then say, okay, is there an open value? Do you have an open activity, in your case? Assign it a time that's 1 minute earlier than that number at the top. Is there a closed activity in your case? Okay, assign it 1 minute later than that. So that gives us the bookends, where open and closed are always at the bookends. Now, to be honest with you, I originally wrote this code with a for loop, which is usually a bad idea in R, and it certainly was. It ran dog slow. So this ugly code actually runs a lot faster. However, if any of you have improvements to it, please let me know. I would love to see how you could do this better and faster. Yeah, that would probably help. I looked at using a dplyr and I just couldn't figure it out, and I was like, you know what? I'll just write some code. Yay. Okay. As I said earlier, there's a lot of data that we have in the event log that we don't really need, because we only need at a minimum 3 things, right? We need an activity, we need a timestamp, we need a case ID, and if we have a resource, that's interesting. So what this code is doing is subsetting down the data to only the columns that we care about. And then lastly, this is a bit of a hack. The ProM tool that we'll see next doesn't have a facility in the CSV import for designating a column as a resource. So the hack is, if you rename it to a common name that it expects, it will automatically recognize that column as a resource. So this code just essentially transforms assignment.group into the name that ProM expects. That's all that's doing. And then lastly, simple file. Again, I'm using write CSV. If you find that morally offensive, we can talk about that later. Okay. Oh, this part right here. So the next tool that we're going to look at, ProM, the Process Mining Workbench, doesn't have a UI feature yet on CSV import for designating that this column is a resource column. So if you just change the name to what it expects by convention as a resource, it'll automatically recognize it. I guess I shouldn't look in the camera directly. All right. Okay. All right. So what we just witnessed is the classic data mining, data science lifecycle, where you spend 8 out of 10 hours getting the data, understanding the data, cleaning the data, getting more data, understanding the data, munging the data, and then finally you get to the fun part. This is the fun part. Or maybe you think all of it's fun. Obviously I think all of it's fun, but your mileage may vary. Okay, so this is ProM. ProM is the Process Mining Workbench. This is open source software, primarily built and maintained by the Technical University of Eindhoven in the Netherlands. It's an open source tool, very, very powerful, has lots and lots of features. That being said, the GUI has a bit of a learning curve. Once you get used to it, you can do a lot of really cool, awesome things with it, but I won't lie, there is a learning curve to the GUI. So what I'm going to do here is, you'll notice I've already pumped in the short stuff already. We'll show you how to import the long. I already did the short stuff because it's exactly the same steps, so it'd be redundant. Okay, so the first thing that we want to do in ProM is we want to import our data. So we click on the import button up here, and we want to filter in the long data because we already have the short. And I'll click open. Now the paradigm in ProM, the UI paradigm in ProM is actually relatively simple. It's based on input, action, and output. So what I've got selected here is something that I want to use as input, which is the CSV I just imported. And the mnemonic I use for the UI is, I've selected something and now I want to play with it. So I can pick the play button, or I can pick the play button. And you'll notice that in the PROM UI, my imported CSV file is now in the input. And yes?
Windows only.
Nope. This is all Java-based. It runs on Mac OS just fine. Or Linux too, if that's your poison. So what PROM does do though is that it's relatively smart. Based on what input you select, it will filter all the list of universe of possible actions and plugins that it has to the things that are applicable to the input. So you'll notice here, ooh, sorry, that's kind of washed out. But what you'll notice here is that this says convert CSV to XES. So XES is an XML format for event logs, and that's what PROM understands. So PROM knows that you want to transform the CSV into a format that it can work with. And you'll see here on the output side, I've got my event log. So we just click Start. And if you've ever done any sort of CSV importing, this UI is very familiar, right? This all works out just fine, so we just click Next. Now what we need to do here is we need to map. We need to map the data in our file to the concepts that we talked about earlier. So the first thing we need to do is tell PROM which one of our columns is the case ID. And for us, that's the incident ID, so I can just add it. And that tells PROM, map incident ID to the case ID, the concept. Over here, we need to do the activity. So we know, wait a second, that didn't work out very well. These things are supposed to be filtered off. Anyway, I'll roll with it. We know, whoops, excuse me. Sorry. Okay, we've got a problem here. Hold on, Houston, we have a demo problem. Scary thing is I ran this thing twice before y'all showed up. Let's try this again real quick, shall we? Ooh. So we have a problem. All right, I'm not going to belabor the point. Potentially. Let's see here. Short dot filtered, long dot filtered. Oh, you just run up. We can just try this here again. Let's start all over. We're not, see, remember what I said earlier, right? It's really easy to mess up your data in R very fast. And then we'll run this. Real quick. Anyway, while that's running, what we would be choosing here is the activity ID. And it's not in there because I've got a problem, which hopefully I'm going to fix here quickly. Lastly, what we need to assign is a timestamp. And what we know that to be is our date stamp, right? That was the value that we had. Now you'll notice, as I said earlier, there's no UI widget for selecting the resource, which is why we did the hack earlier and just assigned it that specific name. And that's still running. All right. Okay. So moving on, we'll just cancel out of that. Conceptually, I'll show you what we would be doing next, which is filtering again. Right? I've already done it on the short log, but I'll do it again because I'm having a problem with my demo with the long data. So we already filtered once, right? We said, give me the 90%, the top 90% of all activities in the event log and filter that down. Cut out the extraneous 10%, give me the 90. And what we're going to do again is we're going to say, look, you know what? I want to filter the event log again to get it even more whittled down to something that will allow me to do something interesting. So how you do that in PROM is, once again, you select the input, which in this case is the filtered short file. Press play on that, and again, you'll see it over here in the input. Right? And you type in heuristics. Whoops, you don't misspell it. And what you'll see here, whoops, is, again, that's washed out. What this says is filter log using simple heuristics, right? And that's a plugin that allows you to go in and, once again, look at your event log and filter it down yet again. And it provides some functionality and capabilities that aren't easy to do in Editor, so that's why I often do this as well in PROM. And we say, okay, yes, we want to keep the start event. Now, The first thing you'll notice is that it says, hey, look, in the short event log file, I can see that there are start events that are both open and closed, right? Remember we saw that earlier when we were doing the summary statistics, how things weren't exactly 1.0 and then there were more closed and then there were open. So this actually makes some sense in the short event log, right? So I say, okay, well, I know from a business process perspective, I know that open is always the actual start event. So what I want to do in ProM is I want to use the slider and I want to select the maximum number of things that I can that doesn't highlight the closed. Because what's highlighted in green is what's going to be considered by ProM as in scope for the first event. And what we know is that closed is not the first event. Closed should be the last event. So I can play with the slider a little bit here. See, if I go all the way to the top, see how closed shows up? So what I want to do is I want to pick the maximum number of events that doesn't include closed. Right there. And what that does is that gives me the maximum amount of signal to noise ratio in the data. So I can click next. Reflexively, it's going to say, okay, look, I'm trying to figure out what the end event is. And what I can figure out based on the event log data, it's one of two things. It's either closed or caused by CI. Now we know from earlier where we saw that closed or caused by CI had the same timestamp sometimes as closed. So this doesn't surprise us, right? If we see this, we know that. We saw that in the data. But we can now clean that up a little bit. We can take the slider and we can say, look, I know from a business process perspective that closed is the end. So what I can do is I can just go ahead and stream this down until the top one is no longer highlighted. And you'll see here, unfortunately, I'm losing some fidelity in the data, right? I'm only using 61% of the possible activities. That's okay, because remember, again, we're going to whittle down until we get a good understanding what's going on, and then we'll iterate back up if we want to. And next up will be crass, and we'll say, you know what? I've already explicitly got my bookends on the process, so you know what? I'll just throw everything in the kitchen sink in there. We'll be cavalier. Yay! And then we'll click finish. And then what that'll do is it'll create a new filter down event log. Now what you'll see here is something we won't talk about tonight, unfortunately. You can also do event log analysis graphically in the ProM tool. It actually has a lot of features. Unfortunately, we don't have time to cover that. One of the learning more resources that I'll talk about later on will teach you about how to do more event log analysis graphically in ProM, in case you don't want to do it in R. But why wouldn't you want to code R? I mean, come on. Everybody loves R. Okay. So now that I have a filtered, yes?
Is there an API for this? Can one call this from R? Can automate this?
So I don't know the answer to that question exactly. So ProM itself is a Java-based system with with a plugin architecture. It's designed to be extended. Now, whether or not it's also designed to have its plugins externally callable via like RJava, for example, in R, I don't know. It's a good question. Is it possible? Of course. I mean, if you're willing to hack the code yourself, because it's open source, you could do whatever you want, right? Should you? Ooh, that's a different question. I don't know. It's a good question, though. An unexpected question, by the way, the best kind. Okay, so again, I'm just going to continue on because of my demo not working as anticipated. So now that I've got that whittled down event log file, what do I do with it? Well, now I can do the moral equivalent of that thing I was talking about earlier, Anscombe's quartet. Let's visualize what the event log actually looks like. And so what I do is I highlight the filtered event log, and I want to play around with it. And I get a long list of things I could possibly do. The thing that we're going to use tonight, and it's always a good one to start with, is what's known as the inductive minor. We can't go into the algorithm because remember, you're not going to be an expert. Don't put it on your LinkedIn profile. Just trust me that the inductive minor is goodness. It's a good one to start with. Now, ProM is extremely powerful. If you're familiar with like neural networks, for example, there are many, many hyperparameters that you can tune on neural networks, which makes them very powerful, but also very difficult in practice to use effectively. ProM is the same way, lots of knobs and dials. So in general, just use the defaults because they've been selected through academic research to give you the best results, generally speaking, most of the time on most data. If you're super interested in this, and I hope that you will get super interested in this, you can study and learn more and start playing around with all the parameters mean. Okay, so we're going to go ahead and mine a model. And this is super interesting. Because the first thing that you'll notice in this model, once you become familiar with it, is that the x-axis represents time. So temporal structure is based along the horizontal axis, right? And what this is showing is that the only temporal structure I have that I can find by mining this event log is open and closed. Notice that everything is perfectly vertically aligned, which means that the data shows no temporal structure for anything else. So if you want to think about this in terms of a website, which is a really good analogy, people are just basically going everywhere to every page randomly. They're just clicking on stuff randomly. Right? This is what this is telling you. And that's very interesting because it's indicative of two potential situations. One, this is legit. This is how people are actually using your system. And I would argue that's bad. Or secondarily, you've got a data problem. Maybe you're not actually recording your event logs at a fine-grained level of detail to actually extrapolate the temporal structure, right? This is a contrived example again, as you well know, I like those. But imagine, if you will, that you had a website that consisted of 4 dynamic pages, right? So the pages will actually dynamically render at runtime whatever they need, but you only have 4 pages, right? But if you only logged in your event log those 4 pages, you'd probably see through a happy path scenario people bouncing back and forth between them randomly because you're not actually getting to the right level of detail. What was dynamically rendered on each page? All you know is they bounce back from 1 to 2 to 3 to 3 to 3 to 4 through 4 to 1. And you may get something like this. That may be indicative of your data problem. So, good question. I was going exactly there next. So, the way to interpret this is these white boxes are obviously work being done by human beings, right? We know that because there are teams. We saw that earlier in the log file, right? What this black box is showing is that this work is optional. I'm at this decision point, right? I could either go left or I could go right. If I go left, I actually do the reassignment work. And if I go right, I follow through a shadow activity that essentially is null. It's nothing. And what this shows is that it's optional. Which is, again, sorry, super interesting. So you'll see reassignment is optional. Caused by CI is optional. Status change is optional, right? Because you've got this and this. You've got this and this. But assignment is not optional. So every instance of this business process, of this event log flow, has an assignment going on. Yes? No, there isn't. It's a good question. The only structure that really matters essentially is left to right, not vertically necessarily. Yeah, I mean, if this was down here, it's fine. What's more important is that they're all vertically aligned, so there's no temporal structure, there's no dependency in time amongst these things. Essentially, yeah. If I understand you correctly, yes. So, from a machine... Yes and no. Because the other super interesting thing here is, what does this show? Ooh, where's my pointer? Oh, sorry. Pointer. What does this show? Hey, closed, I can go to a decision point, which is, I'm done. Or, oh, wait a second. No, you don't reopen it. This is after open. So this is why it's, I mean, I'm sorry, I'm like a kid with in a candy store. This is why it's so super interesting. In theory, what this says is I have an open event, an open activity. I have some stuff that goes on in the middle. I have a closed activity. Then I could potentially have some more work going on, a closed activity, some more work going on, a closed activity. That's what this shows. And I know for a fact that that's not supposed to happen. That would be bad. So it's interesting, right? Now, from a machine learning perspective, let's say I'm going to create a regression model to predict throughput times. I can start using this thing to start giving me some insight into the kinds of features that are potentially interesting. For example, maybe if I didn't do this, I would say, look, I would never need a closed count because there's always only one closed activity. But now I know maybe there's not. Maybe I do need a feature of the count of closed because maybe that, from a regression perspective, is highly accurate in predicting throughput. Now, of course, again, that's bad. I mean, if you're building a model like that, you're accepting a broken process. I mean, there's an argument to say, why are you doing that? But let's just go with it for a second, right? That maybe that's what I would be doing. There are, yes, and it does. Just not with just this visual, not with this visualization of this particular algorithm, but there are many others, many others. And there are ones that will do that. You can use what's known as a heuristics net, and it will do exactly that. It'll give you the relative counts as well. We did. I mean, it was, the percentages were really close, the counts were really close, but there were, probably hundreds. If I had, I'm just calling out the. Yeah. And what this is telling you is that with the data input that you gave it, right, which may never be perfect, this is the best it could do, right? And what it does is it gives you insight. It's kind of like Anscombe's quartet, right? Four distinct collections of data. They all have the same summary statistics, but when you actually plot them visually, they're wildly different. It doesn't tell you why they're wildly different. It just tells you that they're wildly different. So this just kind of tells you that there's something going on here potentially that you didn't expect. And as a data scientist, and as someone who builds machine learning models, this helps me a lot to start thinking about, it gets the juices flowing of what kinds of features I should be engineering and exploring and testing out for potentially creating better and more accurate models. All right. This is the short, because I messed up the long. Real quick, let's see if I can, okay, that all worked. Cross my fingers. Let me run the rest real quick. It should. I mean, honestly, I really did test this a bunch of times. Oops, and then I run the last one. All right. So I'm going to try this again just because somebody asked and because I need vindication. Let's never underestimate the importance of vindication. I'm just going to breeze through this because we already went through all this before. There we go. Now we're cooking with gas. All right, so I'm mapping everything. I'm bringing it in. We're ignoring that because we don't have time. And I'm going to go ahead and filter that using heuristics like we did before. Oops, you got to spell it right. Okay, so this is where things get interesting as well, because you'll notice before we had to pick between the two, but based on our previous analysis, we saw that open was present 100% of the time in the long log. So this jives. Makes sense. So we can say, you know what? Yeah, give me everything. But again, we run into the same problem that we saw before, which is you can't really differentiate between closed and caused by CI. So we need to adjust this down to make sure that we give the exact stuff that we expect, right? And we're at what, 69%? It's unfortunate, but it is what it is. Yep, you're throwing away some of the data. Absolutely, absolutely. And if I seem cavalier about it, it's half the fun of event log mining. Okay? This is where it's good to be an event log miner, not necessarily a statistician. Data. Okay. So your heuristics miner, or heuristic filtering log with heuristics, excuse me. And we'll go ahead and run the inductive on this real fast. And I'm getting over time. I apologize. Again, take the defaults. Wham. Yeah. This is event log mining. Sweet. Much more complicated. The first thing that you'll notice probably is that we still have the same problem, right? Closed. But unlike last time, we've got this guy sitting out here. So we either have 0 or 1 caused by CIs in the longs, which was different than what we saw in the shorts. What we also see is a lot of loops. I can go back. Right? I can go back. I can go back. I can go back. I can go back. So what this means is that what this tells me is, essentially think of this cluster as being the moral equivalent of that very tightly vertically oriented thing that we saw earlier. You still can't differentiate these things temporally. The fact that they're moved around a little bit on the x-axis is purely just a spacing problem, right, for the UI renderer. Strictly speaking, it's not saying this one always happens before this one. They can happen at the same time. They can happen in parallel. And how you know is by the fact that you go from this thing to this thing, and it branches out to multiple things. So what it's saying is all of these things can happen in parallel. And they can happen optionally or infinitely in parallel. Now again, if I was a data scientist trying to create a regression model to predict throughput, I could derive a lot of interesting potential features from all. Yes? Yep. It's an astute question. Astute question from that young man back there in the corner. Yes. Now the problem is that the algorithm itself, even though you specifically filter the data down, the algorithm itself still couldn't actually come up with that definitively, right? Which is why there are so many algorithms actually in ProM, because you will actually get different results from different algorithms on the same exact event log. Just like in machine learning, you may get different results from a decision tree from a logistic regression and classification, or from an SVM or a neural network, even with the same training input, right? Same thing. So very, very good question. Yes, we tried our best to prevent this by shaping the event log, but this algorithm still couldn't figure it out. Now, what you would probably do in practice is you'd probably apply a couple of different other algorithms and see if they produce similar results. Sure. Colloquially, if you want to think of it that way, yes, but the algorithms don't add data physically, right? So
yeah,
it's...
My point is we cut down the data, so that circumstance, as you pointed out, wasn't there. And because of the algorithm, it suggested it might be that.
It suggested it might be there, but we're going to go from a particular worldview, which is these algorithms don't manufacture data and add it back in, right? So I just want to make sure we're clear on that point. That's all I'm saying. Yes. It's potential. I mean, there's lots of reasons, right? But that's potentially possible, right? And so one thing you may want to do is go back to the original event log and say, look, do I have any orphans, right, with opens without close, and maybe I just pair them from the initial event log. We didn't do that because there wasn't time, but you could do that. They,
because you have a loop where you can have infinitely many closed.
yes, actually that's... Yeah, there's... Yeah. Everyone has an open, right? Because in the longs we saw that was 100%, right? So we didn't have much time. So, yes. Yeah. Yes. Yes. This is not machine learning. This is not machine learning. What I maybe I didn't do a good job of articulating this earlier. If I did, if I didn't, I apologize. As part of your tool belt as a data scientist, you may use these techniques to help you build better machine learning models because they allow you to visualize and think about the data in new ways. Yeah. So it's a good question. So we're way over time. So this will be the last question, and then I'll get to the slides, and then I'll hang around for as long as anybody wants to talk to me. And if everybody leaves, I'll be sad. Okay. Imagine, if you will, that what I do is I have my event logs for customer interactions. I'm a bank, let's say, right? And I have customers, and they come in, and they use online banking. They use the telephone customer service reps. They come into the bank, and they talk to people. And I have a CRM system that tracks all of those events. Very common thing, right? And what I'm really interested in doing is understanding what are the patterns of events that people typically do right before they take all their money out of the bank and go to one of my competitors, right? What this technique will allow you to do is start subsetting the logs to smaller and smaller portions of events, and then mine out what those processes actually look like at a high level. And what it allows you to do, for example, is to find out maybe some things you didn't already know, which is, well, hopefully it doesn't look like this, because this basically tells you have really no idea what happens before somebody churns. This would be bad, but assume that this was okay. You may say, hey, you know what? What I notice is that excessive counts of this particular activity is highly indicative of churn, right? And then what I may do is may say, okay, look, you know what? I want to focus my efforts on this particular data point, not the data point, but this particular aspect of the process model. And what I really want to know is, what are the factors that influence whether this thing actually gets called multiple times or not? So for example, I may take the data and I may create a decision tree, for example, just to try and figure out what are the decision criteria that actually makes me go through this loop more than once, for example. I mean, there are lots of things you can do. Lots of things you can do. That was supposed to be the last one. Okay. So if I understand your question correctly, how I would do it, take that for what it's worth, by the way. How I would do it is, I would use this as part of my exploratory data techniques, right? Part of my overall cycle of creating new features, and I would just use plain old cross-validation. I would say, okay, I'm building a bunch of machine learning models. This is just part of my design process, my data exploration process, for me to get the juices flowing for new features. I still need to run my typical cross-validation types of processes to actually validate, do these features actually improve the model or not? Do they make my model overfit? I don't know. You'd have to figure that out. Okay, this really has to be the last one. Okay.
Everything you did in R, while you were doing it, just struck me that I could do all of that in Power BI desktop, aggregate, creating. What can I do? What do I use R for?
So with this laptop, I've worked with event log files with 29 million observations. Power BI, no likey. It's a scale thing. Yeah. Now, Power BI is good because Power BI has embraced the R, right? You can embed R into Power BI. But that's one example. There are many others, right? A lot of instances of data. Yeah. So, for example, even if I got a data science VM with 114 gigs of RAM from Azure and 16 virtual cores, Power BI desktop's still not going to handle the data, but R will start to scale to that. Now, the processing time goes up too. It would be like hit enter, go to lunch, come back, but it would still work. Huge difference between Power BI and R. A huge difference between Power BI and R. Yeah. So to be clear, I love Power BI. I think it's a great tool. It's for certain things, right? And then R is for other things. Okay. I'm over, and I apologize for that. As promised, here are, just real quick, I won't drain the slide. If you want to learn more, if I made you excited, here's a bunch of resources. You can get, this is up in the GitHub, so you can get the deck. This course right here, if you're interested at all, if I've piqued your interest at all from FutureLearn, is free. It's only about a 4-week online course. It only takes about 4 hours a week. It's very high level. It's all in ProM. It shows you how to do event log analysis in ProM. It's a good place to start. And you say, you know what, if it piques your interest even more, then you can get more in depth with the rest of this stuff. So this is a great place to start if you're interested. Okay. Thanks. Hopefully you found this entertaining and educational. And I'll stay as late as anyone would like to stay.
I just finished an analysis on a huge amount of